Thank you so much for coming along this evening to this inaugural lecture by Cliff. And in a moment we'll get underway with that. But it's my duty as Dean of the Bartlett Faculty to welcome you this evening. I'm Jackie Glass, and so it's my pleasure to say a few words at the start of inaugural lectures. Because inaugurals are all about knowledge. They're all about somebody coming to a point in their career where they can profess. And in 2022, Cliff, you were deemed to be able to profess. And you are going to share with us some wonderful learning this evening about characterising homes for the energy transition, which I know is a really important theme across your whole department and your whole institute. So for those of you who don't know Cliff, he's Professor of Building Physics at the UCL Energy Institute, where he leads the Physical Characterisation of Buildings group. He directs the Smart Energy and Built Environment MSc, and is director of the EPSRC Centre for Doctoral Training in Energy Resilience and the Built Environment. And that is where our links go back quite a long way, Cliff, because I was a CDT director at a similar time when you were involved as well. So CDT Centres for Doctoral Training are super important, and I know many of you will have either experience of one, you'll be supervisors. So I'm sure you're going to mention all sorts of things in your presentation which relate to research this evening. Now, Cliff's research focuses on understanding and improving the observed performance of the fabric, heating and ventilation of buildings. He develops and refines methods to better characterise the built environment, aiming to derive actionable insights from measured building performance data to solve real-world challenges in energy efficiency, flexibility and healthy indoor environments. And if that didn't sound demanding enough, what's really interesting from my point of view about what Cliff does is he and his team measure and develop physically informed models to characterise building performance, undertake analysis and relate these outcomes. Here's the really critical and arguably quite difficult bit. They relate these outcomes to the complex socio-technical interactions that affect building performance. So in that way, his research aims to support policymakers, industry, and ultimately consumers. And that whole very integrated ethos for me is really nicely evidenced and illustrated in a recent paper that Cliff co-authored, which was around heat pump adoption in the UK, where he and the co-authors on that paper, they cite the challenge, the specific challenge of there being no central orchestrator of heat pump flexibility. Yet such flexibility could shift electricity loads out of peak periods and reduce whole systems costs. So you can see how important it is to study and to research in the way that Cliff goes about his work. So Cliff, it's my absolute pleasure to introduce you this evening. Welcome, and delighted to hear your inaugural lecture this evening. Thank you.
Great. Thanks, Jackie. I noticed who laughed at the idea of me professing. So let's get going. Buildings. Everybody knows about buildings. It kind of seems very straightforward. The physics seems relatively simple when we're talking about the thermal performance. Heat flows from hot to cold, second law of thermodynamics. Insulation resists that heat flow. And then the occupants need to do stuff in the space. And that stuff might include heating the home. So it all sounds fairly straightforward, and everybody thinks they know how their home performs, or their building performs. Actually, if you're in a UCL building, you don't know how your building performs, and you certainly don't know how to control it. It's going to be quite warm in here by the end, I think. So the issue is, it doesn't quite work like that. At the centre of buildings and energy and physics in the area, we've discovered that we don't really understand how buildings work, and this is kind of a focus for us moving forwards. So a lot of people work on models, and models are fantastic. Models enable us to capture what might go on in the future. So models enable us to work out how a building might perform before you've even started actually building it. You can also use it to test different scenarios. And those scenarios might include how buildings perform as the climate changes and how comfort and well-being changes. So they're essential for planning our built environment, planning towards net zero. And of course, this is really important. Buildings account for around about 40% of UK carbon emissions. So they're a really big emitter, and we really need to understand them. The problem is that when we measure buildings, we find that the actual performance in operation isn't really like what the expectation was, what the models said they were going to be. This is called the performance gap, and it's sort of defined in many different ways, but the easiest one is the difference between the expected performance and the actual performance. The performance gap might be on the overall energy use, it might be on the thermal properties of a specific widget, but it's used very loosely and it's used in many places. And the performance gap isn't small in most cases or many cases. It's often between 30% and 100%. Sometimes I've seen it as high as 200% for whole houses. So it's extraordinarily high. And that forces us to confront a challenge that how can we plan for the future and how can we decarbonise when we don't understand how our buildings work. Fundamentally, that's the bottom of it. We don't understand how they work well enough. And the models are essential. How are we going to be able to trust models in the future? So this is something that I looked at just when I was starting off in this area. I started off developing computer memory. I was in superconductivity and magnetism, it was all very interesting, but actually it's nowhere near, it sounds really difficult, all these magnetic effects and quantum effects, but actually buildings are much more challenging. And when I came into the area, this was one of the results that kind of really made me take note. So, what is this showing us? This is the U value. The U value, if you don't know what it is a measure of the heat flow through a unit area of any building element for a unit temperature difference. So you have a metre of a wall, how much power flows in or out through that. And we have to make sure we can scale it up for different temperatures and so on. So this is measurements of a load of walls, around about 300, I think. And this is what the UK modelling tool was using for the U value of homes at that time. It was using 2.1. And that doesn't really represent many of the walls very well. Most of the walls are brick, so it's this stuff. So we've got none of them that they measured that were there. And even the stone walls, there were quite a small number higher. This really matters. If walls perform better than expected, you say, great. But what it means is if you have a retrofit, you're going to get a lower return on your retrofit financially, and the country makes a lower saving in carbon on the retrofit because it already performed better than you thought it did. Oh yeah, U value. There you go, that's what it is. So this kind of got me thinking, how can the evidence just be this bad? And I was really shocked when I came into this area. How can the evidence be this bad? And it's worth spending a little time reflecting on that. And there are a couple of really good reasons. So the first, of course, is that it takes quite a long time to measure the thermal properties of a house, the way it's traditionally done. It's really expensive. You need specific equipment. It's not that expensive. I mean, I come from superconductivity and magnetism, and it doesn't cost £250,000 for the latest widget, but it's still expensive. But more importantly, it's the time and the skills of the workers. It needs quite specific conditions, and that's really important. So you can only do it in certain weather. And that includes having no direct sun, and you need a big temperature difference between inside and outside. And then it just gives us limited information. You measure a point on a wall, say here, now you know the U value of that point on the wall. I don't know what it is over there. I'm going to assume it's the same, but I don't know. So this is a challenge. And we just have to assume, we only, because it's expensive and it's difficult, we just assume that all walls are the same, all roofs are the same, all floors are the same. And that leads to results like this. Somebody did a measurement once, and that measurement went into the national model, and then they just kept on using it. And it kind of makes sense, but it's also wrong. So the question was, when I came in, can we do this better? Can we find better methods to characterise buildings? And just before we get too far, it's worth just stepping back and saying, is it a problem if we don't know? Well, I've kind of said it kind of does matter for climate change. But this felt like the tip of the iceberg to me. We don't know what walls are, which is the simplest possible element, just a solid wall. Then how do we know anything else? How's that been proven? Where's the evidence? We also don't know how it varies over time and over space. We don't know how individual components scale up into whole systems, and that's particularly important when we're talking about heating systems. And really common problem, you characterise a boiler, and then you're going to stick it in a heating system where it performs quite differently, potentially. And we have to note, it's been really difficult to improve the performance of buildings. This has been a real sticking point and a real challenge for successive governments. However, at the moment, we're reaching a time of change. We're getting a lot of low-cost sensors. We've got smart meter data. And so what can we do with all this new data? Can we have a transformational change in the way that we understand our buildings? And could homeowners actually understand, for example, how their biggest investment that they make in their life actually performs? Which seems like a reasonable thing. A couple of caveats. It's not really very easy to do that, which is why we're working on it still after the sort of 15 years-ish I've been in the sector, and why there's many more years to go. One of the challenges is knowing where the performance gap is. So is it with actually with the measurement? Is it with the modelling? Is it with the surveys that might be done to work out what a building looks like? Is it with building practices or what was sent to the site when it was built? Or is it to do with what people do in those buildings? And over the last few years, there have been lots of articles blaming different parts of this puzzle for different things. I think the one thing that we can say is that the amount of energy a building uses is just the energy it uses. That bit can't be wrong. So what we've got to do is fix all the other bits and look for where the gap is everywhere else. And one of the particular concerns that I've always had is that a few years ago there was a real emphasis on people being a challenge, people operating houses in the way that they shouldn't. And that doesn't ever seem very reasonable to me. A house should be robust, or any building should be robust to the occupants, because it's there for the occupants. So, we're about 10 minutes in, and I've got to the overview slide. We've got 2 hours, so settle down and relax. And I've got some paper. We've got written exercises later, so if anybody needs paper, then, calculators are allowed. So I'm going to give an overview of the research that we've undertaken in the last 15 years. And what I've tried to do with this is bring out roundabout, because I can't remember the number, 6 messages that I've kind of learnt, that I have learnt, as it were, as I've gone along. And so the research that we do, so I should have said what the overview is. So space-time applications and applying the learnings, which tells you absolutely nothing, but don't worry. That's fine, that's what overviews do. So what do? We aim to decarbonise And we also aim to lower costs. Finally, of course, indoor environmental quality, which is indoor air quality, the quality of the air, plus things like overheating, underheating, and noise. Improving these things is essential, and sometimes it can be the environmental quality aspects can be at odds with the energy aspects, where, for example, people keep doors closed, windows closed, when actually they need to open them. So for energy, it's better, but for actually living in the space, it's worse. So that's what we do, and we study every bit of a building you can think of, all the elements, which are the walls, the roof, the floors, windows. We look at the ventilation, we do whole buildings, and we do heating and cooling. So I don't think we've missed anything there. And what we tend to focus on is spatio-temporal heterogeneity, which basically means things that are non-uniform in space, so different in different spaces on a wall, and things that change over time. And we focused on developing new methods rather than providing a number in general. We do a bit of that. It's useful and it's important, but we focus mostly on developing methods. So this talk is basically our adventures in space and time over 15 years. And this is, for anybody who doesn't know, this is Doctor Who reference. Right, so space first, adventures in space. Simple components are complex. Let's start with a fairly simple component, a floor. So we looked at suspended timber floors. Suspended timber floors look like this. So that's the floor. We're in the void under the floor. These are the rafters holding up the joists holding up the floor, and they're resting on walls. So it's suspended. There are somewhere between 6 and 10 million in the UK. We don't know how many, so we don't know lots of things. So I thought, quick show of hands, who would let us come and measure your floor? And who's interested? Okay, that's really positive. So now, who would let us come and measure your floors? Oh, a few. Oh, I'm excellent, brilliant. So the problem is, it's incredibly disruptive to do this work using traditional methods, and so this means it's incredibly hard to gather evidence. So you can immediately see that with difficult elements, like floors in particular, where we need to walk over them, we need access, we've got stuff in our houses. It's really difficult to do this. This was on an unoccupied house, which was the only reason that we could measure it. So it's really difficult. And when we started working on this, there'd been very, very little work done in the UK. And what we found was this huge variation in thermal performance spatially across the floor. This makes total sense. So here's the floor. This is the outside wall here. And this is an inside wall. And what you see is towards the outside wall, there's lots of airflow. It's quite close to the external wall. And so you've got a really high U value, which means high rate of heat flow. Whereas a long way in, you've got a really low U value here. And there's about a factor of 4 difference across a single floor. That kind of makes sense to us. But the problem was that was about 2 times worse than modelling said it was going to be when the result came in. Which is interesting, actually. A lot of our research has found better than expected performance. This one was worse. Worse means that it's more valuable to retrofit it. And so the retrofit with insulation, and this is the same floor, and these are big, kind of solid pieces of insulation that have just been pushed onto this matting, which is there to keep it structurally sound and to reduce airflow and things like that. So really effective, but also incredibly disruptive. So we did quite a lot of work in this area for a few years. You'll have noticed that there aren't a large number of retrofits, and we'll come on to one of the reasons why in a moment. But here's a different element that should be easier, because these are roofs, and so at least you don't have access problems to put some equipment on there. You're sticking something on a ceiling, so but you can still use the room completely normally. Turns out there's very, very limited evidence of the thermal performance of roofs as well, despite the fact that there have been major government programmes of retrofitting roofs for the last 30 years. And yet they don't know what the performance is before, and they don't know what the performance is after, which is troubling. So here, this is the kind of thing that we see quite commonly. These are thermal images, and blue is cold, red is hot. And this is the ceiling, and this is an external wall, and we can see it's cold there and there. These are defects here. You haven't quite got your insulation pushed into the end of the roof. Here you've just got a gap. And here, this is actually a bit of sloping roof where it joins the flat bit. And they've just not done a very neat job of it, and it's just sliding down there, and there's a gap where it started to slide down and take the stuff that was attached with it. And it looks like this, it's messy, you know, that is a gap that you can get your hand into. But this shows you one of the big challenges in the sector. So I'm a believer, if you study a part of a building, you should go and touch it and feel it and see it. And if you've tried to fit loft insulation into this so that you can actually get to the edge to close that off, it's really difficult. And if you are too rough with it, you block the ventilation. So then you can have problems with damp in your loft space, which is worse. Pitched roofs are a challenge. But interestingly, the void itself, just this bit above the insulation in a pitched roof, so you've got your insulation there, you've got this bit here. It was assumed in the models that the performance, or it still is assumed in the models because they've not changed it, the performance of this bit in the void was really bad. Actually, it's not that bad. And it really does contribute to the thermal performance of the whole structure. And that largely counteracts lots of these defects and gaps. So that overall, our conclusion was they actually perform about what you'd expect to. They just don't do it the way that you would expect them to do it. And what we should do is we should get rid of this stuff, because that's where condensation is going to form, and that's where you're going to get damp and therefore mould forming. So that's not good stuff. And whilst we're on problems, one of the things we need to think about that we're going to come on to a bit later is managing risks. So one of the problems with doing stuff on buildings is that you tend to create problems as you try to fix them. And some of those issues might be to do with the works that you're doing, but some of it might just be over time, you've got a leak from a washing machine or a leak from a downpipe from guttering. These are incredibly common. You see these all the time. And then this can seep, in this case, under the floor. And you have two challenges. One is, how do you find out that there's something wrong so you can do something about it? And two, if you've insulated it, it might make it better or it might make it worse. And we can't actually tell you in advance which it's going to be because it's quite specific and the research hasn't been done yet. So we looked at as many floor voids as we could, and we actually saw a really disturbingly high number of issues. So this was one of the very few where we saw mould. So this is white mould on the wall. That's really problematic. That's going to seep up into this. The whole lot's going to go rotten. If you're living in the space above, it's linked to asthma, chest infections, all sorts of diseases, even heart disease. So really problematic to get the mould spores up there. This was caused by a leak somewhere in this pipe. It just sprang a leak. So how do you create homes where you might stand a chance of catching that That's really challenging. But there are opportunities with the kind of sensing technologies that are coming forward if there's value placed on identifying them. The problem is the incidence is very rare. And the sensing level required is very high. So this is problematic. You need a lot of sensors to find a leak like that. So that's a pretty big challenge for us. One of the keys is that we need to improve the way that installers do insulation and the way builders work, and there's a lot of work going on that. A lot of work on quality assurance, which is where some of our methods come in, and some cheap sensing potential. And this is something that I'm really keen on at the moment, is the idea of cheap sensors that aren't accurate sensors. But all they're there for is just tell you, is there a problem? Is there something that I should call somebody in to have a look at for me? Because then you can get somebody in to do a proper job. So that was space. Time. And we spent most of our time on time. So dynamics is where it's at. It's where all the groovy kids work. So incumbent methods of trying to determine the performance of a building just try and get rid of the variability of performance. So what they do is we adopt what's called a pseudo-steady state, which is sort of basically means it's a pretend steady state, where we average variables over time intervals. So it's really common. So here, this is temperature, internal, external, just a daily average. That's really commonly done. And then at the bottom, we've got the solar and the power use of the house, just daily averages, which is kind of useful. It tends to lead to very robust solutions. They don't vary a lot when you add more data. They're quite stable solutions normally. And they're very simple, very easy calculations. You could almost do it with pencil and paper. And the methods were developed when computing power was much lower than it is now and really didn't move on for a very long time. But is that really how houses operate? And it does feel like we're throwing away a lot of useful information, because that's what the same data looks like when actually drawn out on as kind of a sensible time interval. I have to confess, I don't know what the time interval is. It's about half an hour, 10 minutes, half an hour-ish. Yeah, Francis says half an hour. Half an hour. I could have asked, but it doesn't matter. It doesn't matter for the purpose of this. When we're doing our analysis, it really matters. So it's the same time, and in particular, we note that there isn't a lot of sun overnight. There are periods during the day when energy use is extremely low and the house is in a cooling mode. That might be useful to know that the power use has gone right down, and we could actually look at how it cools. And that the temperature variations, both internally and externally, are really quite variable. So we started to look at a dynamic approach, and so we've here. This is the simplest dynamic model that we use, and this is treating the wall. This is a cut through of a wall, and it's treating it as having a heat flowing through it with an internal temperature and an external temperature. It's got some heat stored within the fabric of the wall. We call that thermal mass, and that's somewhere in there, and it's got a resistance between it and the outsides. So we don't know where it is, and we've not specified where it is. So we use that and data like this plus heat flux data and some science, which I'm just not going to go into, so just science here. And we get results like this. This is slightly complex, but what this is showing is that the blue line is the incumbent way of doing it, with just daily averages. And the lines, the vertical lines here and here, are the standard stopping criteria that are adopted in the international standards for when you can say that's the value, stop measuring, you've hit the value, it's stable enough. So if you use the incumbent method, it takes 2 weeks. But if you use a dynamic method, it actually only takes 3 days. So that might be useful. There are some other things that might be useful. Dynamic methods can actually account for direct sunlight on a structure. I don't know about you, but my house has some building elements that actually sometimes get the sun on them. With traditional methods, you can't measure those. You just measure the ones that are in the shade, which is very restrictive. Also, all this variability actually helps us get the error right down because we're looking at how things change in response to signals. That means that we can use a lower internal to external average temperature difference. That's partly because at any point in time, it's all varying. So this reduces the error. Averaging tends to bring the average values close together. When it's variable, they're often quite different. At any instant, the difference is higher. So that helps with that error, which means that we can measure in lower internal-external temperature differences. And we manage to do this basically all year round. We just measure all year round and get a reasonable value for most of the year. Just got the time to reach an answer goes longer, the hotter it gets, basically. But it kind of works. That also means it's much easier to schedule. So you can just do it when you've had your retrofit. You don't have to wait till winter. It doesn't take as long if you are in winter, so it's quick to get in and get out. And then the final thing that you can do with this is you can characterise where the thermal mass is. By which, what we're trying to say is, if you've got a wall, and consider a wall that might have brick on the outside, and then a layer of insulation, and then a really thin internal structure with some wood and some plasterboard. For that structure, almost all the thermal mass where the heat is stored is in the outside bit of the wall, not in the inside bit of the wall. The inside bit is very low thermal mass. Thermal mass is important because it damps temperature variation. It slows temperature variation down, which is really useful for keeping conditions good. So we want to have relatively high thermal mass structures where we can. And knowing where it is in the wall could be useful. It might inform retrofit strategies. If we can say, oh, it's near the outside on this wall, we might say, well, let's be careful over the retrofit. Let's put some external insulation on. We might say the thermal mass is huge. You don't need to worry about it at all. Put it anywhere. It doesn't matter. We might say, oh, it's on the inside on this wall. That cavity wall insulation that you've got planned, that'll be fine. So it just provides extra insight that might help us with retrofit. Completely different topic. So this presentation is totally smooth, transitions between topics. So boilers. My new boiler is 95% efficient. Perhaps. So we did some work with simulations and with measurements. And it turns out that real heating systems don't just sit in a steady state and just on, nice and constant the whole time, as was assumed for the majority of the way that they're tested to work out their rating. So if you oversize a heating system, which we do, so these are the average heating demand over a set of properties for a year. So how much heating is needed? And this is the average size of boilers that are installed in the UK. So there's basically only 2 different sizes installed, and they're massive. This is a bit of a problem, because what happens is the boiler comes on and it blasts out heat, and then it goes, it's too hot, I need to switch back off again. And then it comes back on, and then it goes back off. And that's not efficient. That's not a good way to operate. One of the reasons why they're so oversized is because actually, despite the fact we mostly use our boilers for heating our space, they're actually sized for hot water, which is problematic at times. So we were really commonly seeing more than 50 cycles on and off during the day. Some had hundreds and hundreds. This has an efficiency penalty of somewhere between 6 and 9% in the cases that we looked at. So that's increased emissions as well, and methane, because every time you switch a boiler off, before it switches back on again, it purges whatever was in the combustion chamber to set fire to. So it just sends that bit of methane outside. So if you're near a flue for a boiler outside and you can smell a bit of gas, it's because it's cycling on and off, and it's just purged it and just sent it straight outside. So instead of 95% efficient, 86% efficient. And this is a problem, as I've said, because boilers and heat pumps typically are, the way that they're tested for efficiency doesn't necessarily reflect real life and how they will be run by the people living in the home. Additionally, if you've got an individual boiler, as soon as you put it within a heating system and you've got it limited by the size of radiators, the way it's connected to the pipework and so on, it performs differently than it performs in a lab, and that's quite challenging. So this was some work done with George Bennett of DESNZ fame now, and we looked at how to change the sizing, how different controls, optimizing the way things heat up, and just better overall design might help the way that boilers are sized and installed. And there's been a consultation out, and apparently our work feeds really well into that, the new work that will be published at some point in the near future. So ventilation is another one of these staggering things, is that we know from living in buildings that ventilation is really variable. But typically, when you measure it, you give a number of air changes per hour, and you just measure it over a couple of weeks, maybe a month, and you just give an average value back. How can a single number give us really useful insights on something like ventilation? It might be able to tell us something about the energy use in a very broad sense, if conditions are fairly stable, but it's really not telling us a lot about the indoor air quality, because we've got no idea when anybody was in the house in the first place, and therefore whether they were exposed to any problems or not. So the vast majority of work on ventilation is using this steady state average rate. So we did 3 different projects on trying to characterise ventilation. So first thing to note, just before we leap on to some exciting graphs, there are two separate things going on which have linkages, but one is that there are physical things that change the rate of ventilation. So things like the wind and the indoor-outdoor temperature difference. Both of those change the rate of ventilation, particularly in the UK, where the vast majority of our ventilation is natural ventilation. So just windows and trickle vents and things. But the other thing is people live in them and work in them. And of course, those people do stuff. And they might open windows, but they might also mess with the internal doors. And the way that it's simulated usually assumes a set state for the internal doors with no transfer through it, or perhaps limited transfer. So these are quite big assumptions as to what might be going on. And of course, there are different sources of pollutants in different homes, and moisture, which isn't quite a pollutant, but sort of matters because of damp and mould. So here's some results. 2 graphs. This is one house, it's the same house. This is about 3 months. What this one is showing is the ventilation rate as the number of open windows changes. So when there are 0 windows open, we measured ventilation rate within this range using dynamic methods, all based on metabolic CO2, so the CO2 that we breathe out. So we use that to characterise ventilation. And we found that with all the windows closed, it's quite low. That's the assumed limit for healthy homes. With one window open, it's higher, and 2 higher again. So that's that one. This one is, over the same period of time, how often were the windows in those states? So it's split up so we can see the difference. And we see that the vast majority of the time has got no windows open, with a small amount of time with 1 and very little with 2. It gets a bit messy here. It's hard to see, but the proportion is very, very strongly in favour of no windows open. There might be lots of reasons for that. There might be lots of really good reasons for that. And this is where we need to bring in the social factors. People have different reasons why they choose to open windows or not. And those are very reasonable reasons because it's their home or their workplace. So why shouldn't they be able to open the window? Because they like some fresh air. So we need to understand what they're doing, and we need to understand why they're doing it, and whether we could improve the energy use or improve the internal conditions. And critically, whatever the solution is needs to be robust to whoever is living in that building. And with ventilation, it's easy to get it really wrong. So design really airtight buildings, and then the occupant turns the ventilation off because it makes a noise. And they're left in something that's really unhealthy to be. It's quite energy efficient, but it's unhealthy to be in there. So another smooth transition. And so this one is now so I've shown just a smattering of results from different topics. Now what we're doing in the next section is we're trying to apply physics to do something about national policy and practice. So how do we use physics methods to direct with the goal of, rather than let's just understand it, with the goal of informing a policymaker or informing somebody who might be designing a home specifically. Condensing boilers. Right. So, in 2005, on the 1st of April, you couldn't install a non-condensing boiler in the UK. They all had to be condensing, and that caused a kind of step change in the rate of installation because they cost a little bit more. Not that much more, but a little bit more. And the rate of installation before that date was really slow. And then there's this sudden pivot up, and the rate just goes straight up because that's all you're allowed to put in. Turns out that if you're trying to apply physics to policy stuff, that fixed points in time are really, really useful because you can just say it changes there and then model it. So we did that, and I'm going to give you a smattering of results and then a graph to highlight what it looks like. So the first thing is that this condensing boiler policy, which was criticised quite widely when it was brought in by quite a wide range of different groups, because they cost a little bit more, saved half a year's worth of gas boiler heating emissions in total between 2005 and 2013. That's quite a lot of energy in the scale of the UK. They pay for themselves incredibly quickly. We were also able to do all sorts of things that might be useful to an economist, like the energy price dependence of gas heating use, and we could work out general efficiency of the stock. Big advantage of this is that it's really clear and unambiguous as a rule. You're not asking people to choose or decide or think what the best solution might be, which is what most building regulations are about. It's like a menu. And you get to choose as long as it reaches a certain value at the end. Well, that's kind of all right, but everybody on this menu is looking for the cheapest possible thing. Whereas if you just say, well, you've just got to have one of those, it's very effective. It just does the job. And we could produce scenarios. So this is the number of gas boilers. It's difficult to show because there were some changes in the way it was measured. So before it's very slow and then suddenly it goes up. And then we've got total number of homes and the number of homes with gas because that changes over time. And then we forward cast it and we also said what happened if you delayed your policy. So that we could go back to government and say, if you had delayed, this is an idea. Nobody's saying that this is accurate, but this is an idea of the kind of savings that you've made by implementing it now and what you might have missed if you'd done it later. So I guess we could do a show of hands. Who thinks that was popular with policymakers? We've got a few people think it was popular. It was really popular with policymakers. This analysis was one of the first to try and really nail whether a policy like this was absolutely measurable results in national data. And they really liked that. Very powerful and very useful. And it also made me think, shouldn't we be talking about successes more? We criticise our governments a lot, for good reason, but sometimes they do things that just work and are great, and we completely forget that they did it. So perhaps a little bit of balance where we talk about the things that have worked as well as the things that have failed. In the buildings community, we really focus on the failures. And for good reason, because you need to fix those. But there are a lot of things that go really well, and we should perhaps be talking about those a little bit more as well. Airtightness is another application. So the idea of ventilation is that you choose when and how you ventilate. You don't just have leaks in your building, just holes in the fabric where the wind goes in and out. So airtightness is therefore used as we call it a proxy for build quality. So if it's nice and airtight, it's been built as it should have been, is the idea. And that was made mandatory in 2006. So how do you do it? This is called a blower door, and it's just a massive fan in a blanking piece that you put where a door goes, and you just pump air in and out of the house to quite high pressure. And then you just see, how quick does it leak? And from that, you can determine what the rate of leaks is. You always do this with the standard methods with the ventilation closed. So it's not telling you about the ventilation. It's not telling you whether the air quality is going to be nice. It's not telling you whether you might have a comfy home or not. It's just a measure of was it built as it was supposed to be built. So we managed to get hold of the database for airtightness testing in the UK, and this is it for 2 years, 2015 to 16. That's 144,000 homes, so quite a lot of homes. And these are homes that were built to target a leak rate of 5 metres cubed per metre squared per hour. I mean, it's a horrible unit, but 5. And so these are standard and used widely. So anything on this side has passed, and anything that side has failed. So this is the first test. They've finished the house, the builders have done their job, they bring in the airtightness tester and say, give us a test. And most of them hit it first time, and is that good news? It kind of looks like good news. I mean, you've got the result that you wanted, except that normal distributions don't look like that. They don't have really sharp drops on them. That kind of means that somebody was there trying to make it hit. And so you go into homes and you find things like this. So that's what it looks like normally. This is around the electrics for a home, and there's a massive hole in the back there through the wall. And they just stuck a big piece of tape over it while they were air tightness testing. And they'll run around with sealant guns and things and tape, and they'll just tape it up and seal it up just for the testing. And then they leave. Actually, they pull it out before they leave because the customer wouldn't want to see that. So by the time the customer's in there, it's bad. And even if they leave it there, they put it in with the sealant gun, it doesn't last very long. So, yeah, houses miss the point, but they're kind of missing the point of why this test was introduced. This is the process not working. And there's lots of things that you can do to try and improve that with spot tests and so on. And in fact, that's what they're doing in Belgium now. They're doing spot tests to try and check that it's right, giving the first-time test that it should. Because I don't know about you, but any builders that we've ever had in could definitely not hit a target that accurately. I mean, getting a wall in the right place has been a definite plus. But there's some good news, because they brought this in, and actually we have seen a significant improvement in the airtightness of homes. So, okay, it's not at the level it's supposed to be at, but actually it's definitely made an improvement. So we've got to be careful when we bring these things in, that we say testing isn't a panacea. It's not going to solve every problem, but it can help, and it can raise standards, and it can prove things. But it does give us a challenge that we need to think about right at the end of this talk, which is how do we do both? How do we make sure that our tests are doing exactly what we want them to do? Simple answers are useful. Okay, so I've talked about lots of complex stuff. How do we know if we can turn a heat pump off? Because you don't want to use electricity during a heat period in the evening. Sounds kind of complex. I've said it's lots, the models are complex. They don't necessarily work that well. It's quite hard to do. And cooling of buildings really isn't simple. You've got heat in radiators, you've got appliances, you've got people doing stuff, you've got internal and so you've got external temperatures changing at the same time. Lots of stuff going on. So we kind of asked the question, perhaps we should just do something really simple and just measure how quickly it cools down instead. And that might be useful for a customer. So here, how much does it cool down in 3 hours as a measure? But you could change that. You could say it's an hour, or how long does it take to get to a certain level? You can cut this lots of different ways. So this is really simple insights based on physical principles. But because they're simple, everybody can understand how if I turn my heating off for 3 hours, it's going to have cooled down by whatever on average. And you might say, well, we'll do it for really cold and we'll do it for other seasons as well to give people extra insights. But so this can have value. And we're going to come back to simple. But the problem is, as soon as you try and do something simply, you hit into complexity. So this was a COVID study. So it was kind of challenging to do. We got the opportunity to study 3 heat pumps. We didn't choose them. We just found, Jenny found 3 people who were willing to have heat pumps measured in their homes. And it turned out they were controlled in 3 different ways. One of them, you just turn down the thermostat. One of them, you turn off the heat pump. And one of them, you turn down the temperature of the water in the heating circuit. And you get really different savings during the off time. So if you turn down the thermostat, it's mostly off, but by the end, the house has cooled down, so it starts to come back on. If you just turn off the heat pump, it just turns off. But if you turn down just the temperature in the heating circuit, it doesn't stay off very effectively at all. So and you've got to add to this that I've said systems matter. So you've got the heating system within the home system. So we've got the fabric and everything. So it could be that this house at the top was just really, really thermally bad. And it's going to be horrible if you don't keep that off. And so how do you inform the consumer? How do you put them in control and empower them? One of the keys is that if you are the customer, if you really want to minimize your energy use, you really need to know what's going to happen. And if we studied 3 heat pumps and got 3 control strategies, we probably have a problem. There is no UK way of doing this. So when the time comes in the not that distant future, when we have more call for being able to turn off things like heat pumps during peak hours, we may or may not be able to do it with the systems that have been installed, which is highly problematic and something that we need to be looking at. So this isn't really, so this is to inform the process of putting in a heat pump and to think, should there be a standard way of controlling? Always with the customer in charge of what happens, but a standard. Flexibility would always be choices, and we would see it absolutely being tariff-based. One of the challenges being you really don't want to penalise those who can't afford to improve their building or whatever it might be. So really difficult to do, but important to understand what's going on behind it. So the final section, whole house performance and what I have learnt. So we've had a whole load of different topics as different parts of mostly a house. Now we're going to put it together into a whole house because we've been doing lots of work on whole houses for about the last 5 years in particular. It's been a hot topic in government, which has been great. So first off, who wants to know and what do they want to know? There are lots of different reasons that you might want to characterise a home. So perhaps you are planning a retrofit, or you've got a new home and you want to know how it is and you want to know that it works okay on an ongoing basis, or you're having a retrofit done and you want to know how it performs afterwards. Was it done as expected? Perhaps you're a policymaker and you want to know whether your policy worked or not. Or you're a home buyer and you want some kind of rating for the home. Or finally, you might be offered finance for having the retrofit done. And that might be based on the performance. And there's potential market in retrofit finance. So it becomes apparent it absolutely isn't one size fits all, which has been one of the challenges in the field. Is lots of people have really been pushing in one direction for one method that's great, but actually it needs to be tailored for each individual one. It doesn't need to be one method that does everything. And a learning for me was that we can be really poor judges of what other people think might be valuable in the research that we do. 2 examples. A simple method I'm going to show you in a minute to characterise the thermal performance of a house. We weren't pursuing it at all until we were asked to do it because government found it really useful for some of their assessment. And another one is one of the papers that we almost didn't write because they thought it was too boring, and we called it the boring paper. Won an award from CIBSE, the Chartered Institute of Building whatever it is, service engineers, and it changed building regulations too. So it's really difficult to work out. Academically, it just wasn't very interesting, but sometimes things have a really big impact. So engaging with others is important. Another thing that we're really interested in is thinking about tools in terms of do they help research or do they help deployment? Lots of academic work goes on trying to develop tools for research purposes, which is great, but probably mass market is where the real action is. Wouldn't it be great if we all knew how our houses performed in advance of buying them, and then after we made changes to them? So that's perhaps where we want to get to. So simple can be useful. This is what's called an energy signature method. So you just add up all the energy going into a home through the smart meter, and then this is external temperature. You plot a graph and some straight lines through it. And the gradient tells you the requirements as temperature changes for heating the home, and you can, from that, you can work out what's the thermal performance of the home. Really simple, totally unintrusive. All you need is remote data. And you can add axes. This one's got some solar on it. It's rotating because as it moves there, you can see the plane better. So when we do these 3D images, we try and make them rotate, because otherwise it's impossible to try and understand what it's showing. And it's basically, it's a regression in 3 dimensions. But we can do them in as many dimensions as you like. It's just, I can only plot up to, I can only plot up to 3. I can't plot anybody, but Jamie can plot 3. So we deployed this. We did evaluation of the Green Homes grant that you might remember from about 5 years ago. Really big government announcement, Green Homes grant, throwing billions into it. And what we found was, when we applied this to about 2,500 homes with all sorts of different retrofits, that firstly, the houses performed a lot better than we thought they were going to do. So this is predicted. This is our results. And EPC, I can never do the colours on this, is up here. So that's the model. These are the real methods. EDF did some, we contracted them to do some with their method too. And this one's our method here. So first off, houses performed much better than they were supposed to do. That means your potential to save energy is much lower than you thought it was, which is good, but problematic if you're trying to achieve policy goals. And we could see it across all sorts of different measures, and there's just so much going on. I'm not going to go into it in any depth, but lots to learn from there. And there's a huge report on the government, on the DESNE's website, if you're interested. But there are other simplifications we might take too. So one of the things we're interested in is forget about thermal characterisation. Just say, how much is the energy demand from the grid? Let's just forget about everything and just say, if you make a change, perhaps it's solar panels, perhaps it's retrofit, what's the change in energy demand from the grid? Because in the end, that's what matters to the consumer, and that's what matters to whoever operates the grid. So perhaps that simplification, again, which gets rid of a whole load of the problems, might help us give useful answers to some of the people. Okay, so nothing is static and people matter. So the weather changes, buildings change, and people need to be able to do stuff. The traditional steady state models have their value and are very useful for giving you an average performance. But if you want to know what conditions are really like at any time, they're not very useful at all. So thinking about dynamics, super important. And dynamics can also bring some really useful insights. So this is a thermal performance of a home. This is modelled versus measured temperatures. So the dashed lines are our model, which uses some measurements and attempts to map across it. And this was what was actually observed. And it's not a bad fit. And from this, we got a pretty good characterisation of the thermal performance of that house. Also tells us something about the way it heats and cools, because we've learned something about the thermal mass. We did some internal temperature flows ones, which again we didn't know what to do with them, but sort of did them, and it turned out some people were interested in that, so that was quite useful. What's interesting about this graph is this is when traditional methods don't work. So this is April. So you wouldn't use a quasi-steady state model, a static model, in April because it's too sunny and it's too warm. Whereas this model is absolutely fine. It's happy as you like. And the results are nice and stable still at that time of year. So the next question is, can we extend it? Can we take it further? Could we get methods that will work all through the year? Now, these methods are not likely to be simple methods, but can we do it? Details. So we tend to talk about thermal performance in quite vague terms that aren't necessarily useful. So we want to know things like how repeatable is it, how accurate is it, and what does that even mean? Because what do we even compare it to? We want to know what can we use methods for. If the performance isn't as good as possible, what we really want to know is how do we diagnose it? And then how can we fix it? Should we be looking for other things while we just happen to be there, taking some data? Could we just measure some humidity and just do a safety check for damp and mould? And always, are we actually giving people what they want and need? Finally, something that I'm really interested in is can we develop an industry in this area, which is what government is trying to do through their SMETRs program, Smart Meter Enabled Thermal Efficiency Ratings. It's sort of catchy as SMETRs, but really not any other time. And so they've had quite a decent-sized program of research in this area for the last 5 years. Key question is, can the UK create an industry on this, where people trust it and find it useful, gain insights from it? And it was going to be trialled on ECO this winter, but that kind of hasn't worked out. But there is more going on in the area. So to summarise what I've learned, it doesn't look like very much. It feels like more than it looks. I haven't planned what order to do this in. Let's start down here. So firstly, I want a method that I can use any time of year. That's pretty obvious. I just want to be able to plug it in and go. I want it to work on every type of home. That's really not easy. Getting the thermal performance of high-performance homes is very, very difficult. I want minimum disruption for most homes. I want it to not go crazy when somebody opens a door or a window or something small changes. And that's one of the big challenges with the dynamic models. When they work, they're brilliant, and just occasionally it goes right over there. And it's really difficult to work out how to make sure that it gives you a nice, stable value. I want it to be deliverable at scale. Now, this is something that we're really interested in, is the deployment part of this. So can we come up with methods the analysis runs remotely. We can all kind of see, oh, you can just feed it into a computer. But could we come up with methods where actually installing the equipment, those kind of things, that is largely de-skilled? So it doesn't take somebody with a PhD to do it, because there just aren't enough people with PhDs to do this on enough homes. We want it to be repeatable. Accuracy meets application needs. I'm hedging with, because sometimes you don't need something accurate. Quite often you don't need something accurate, in fact. And something that really helps interpretation. We want to get proper insights from this rather than just a number out of it, which tells us very little. We want to be able to diagnose a fault. We want to understand the social dimension. We want to inform modelling and improve the match. And in an ideal world, it would always measure for every home, like in a car. And in any modern car, it's constantly giving you your fuel economy. And it's quite reasonable to say, why don't homes do that? That would be really useful. You could see what happened when you did different things. And that would give real insights and really empower homeowners. So we've got a long way to go. We're well on the route to do this stuff, but we've got a long way to go to get there. So almost finally, all these people contributed to the work presented today, and thanks to them. We've been really bad at getting good photos of the team over the years, so I think must do better. And I wanted just to put something up to show that it does have a real world impact. This is kind of all of our stuff. So we've got all sorts of stuff with supporting government on different schemes. We are on different steering groups and working groups for different parts of government and NGOs and so on. We've won 3 medals from CIBSE. We're currently leading an IEA EBC Annex, which has got a really snappy title. I think I might have had a hand in that. Never ask me to name anything. It's like it's not my place in life. I'm just not good at that. We've changed building regulations, and our work on boilers is really feeding into the changes that are to come. So thanks for listening, and thanks to all my collaborators and colleagues. And there's my stuff if you want to get in contact. Thank you. Are there any questions?
I have a question about your research on boilers and the fact that most boilers here in the UK are oversized and they cycle on and off. Have you done any work looking at modifying the flow temperatures so that the temperature rise is very slow, and so the boiler instead of cycling on and off will stay on for quite a while until it reaches a set point? Do you have any insights into that?
Yeah, I think the rates being slow, but also, so what a boiler does typically in the UK is it can modulate at different levels. So it has a highest power of, say, 26 kilowatts, but then it will usually do 3 to 5 different levels beneath that. So it will do, say, let's call it 25, and then it will do 20, 15, 10. Often it doesn't go that much below 10. Sometimes you might get around 5. But if you go back to the graph, if I could remember the slide number. Oh, that was it. Stop. So there's an awful lot that are right at the bottom of the modulation, and the boiler just can't run constantly and hit that, which is really problematic, and trying to reduce that. Have we done any work on it? No, it's really difficult to get funding to do anything on boilers because they're fossil fuel. So we tried to bid for funding to continue work on boilers, but unfortunately it wasn't going anywhere. It's a shame because there are some quite easy wins that could get you potential reasonable savings, and we've got millions of boilers in the stock, so anything that we could do would be useful. However, government has continued to work on it, and I think that the changes that are going to be announced soon will address some of those things. They're certainly designed to do what you say.
Thank you, Cliff. It's a really great lecture. I particularly liked the last bit about how can you develop the dynamic method to be a trusted service. And I guess what I'd like to explore with you is the current installation rate for heat pumps is very low. It's a few 100,000 so far, and we've got to double that at least to stand a chance of making serious inroads into the gas boiler market. How are you going to safeguard the fact that you'll be building a database in the area of heat pump installations based on people generally who know what they're doing and occupants who generally are, if you like, better able to understand the information that's being provided? And I'm just concerned that if you've devised a method which is great for well-informed and that includes occupants and installers, how is it going to work in the mass market when speed's going to be of the essence to a small installer and the poor occupant won't know anything about these efficiency issues that you've been describing?
Yeah, if there were an easy fix to heat pump performance, yeah, it might be here, but yeah, it's very complex. I think that when it comes to getting the performance standardised, I think one of the things that we will see going forwards is much more consistent performance anyway. That's a natural change because they're using they're using new refrigerants, and the high temperature heat pumps actually are best run at low temperatures, but they're much more robust to it not being set up quite right, which is useful because you don't have to have got that flow temperature just right. It can be a bit more variable. There are a whole load of other problems, and it's very difficult to see a simple solution to it. I think really clear diagnostics and a user panel where, you know, you paid for this. I think every heat pump should come with a display on it that says, you know, this is what we promised and this is what you're getting. So that if it's not where it should be, you can get the installer back and they can come and reassess it. Now, obviously, you know, they're going to have to be careful to put that at a reasonable level. But I think that would really de-risk it if you were entitled to that and if it were linked to a policy around you're entitled to have them come back. You don't have to pay lots extra. It's just implicit that when you have a heat pump installed, it'll perform to a certain level. And if it doesn't do it, it's really easy to call them back or raise a complaint if they're not doing something about it. But it's difficult. Industry doesn't want that. So there's always this tension of what we can do compared to what industry might allow to get through.
I have a question that kind of links the first and the second question. I was quite interested to see your research on boiler efficiency, like the effective boiler efficiency is 86%, not 95%. I could imagine a very similar story being told about heat pumps. You know, they're not delivering the COP that we anticipated. Has there been any preliminary research on, you know, assessing what the effective performance of heat pumps are in the same way that you did for condensing boilers?
Yeah, there have been some quite big projects on that. There was one, it's more than 5 years ago now, and it was the Energy Saving Trust trials, and it was shocking performance. They had heat pumps that were performing exactly the same as a resistance heater, and you just paid for a really expensive resistance heater in your home. Didn't have many of those, but the average performance was very disappointing and much lower than expected, with really complex reasons behind that. There have been lots of follow-up projects, and there's a lot going on it at the moment. We're not doing any sort of really big ones at the moment through EDOL, which is one of the projects that we're part of, run through UCL by Taj. What that project's doing, it's gathering smart meter data from lots of homes in the UK and also a bit of temperature data. And then there's a lab which is on heat pumps, which is run by Jenny, and that is studying heat pump performance. That's actually, because there have been quite a few trials in recent years, and now there are companies with lots of data as well, the angle that that's taking is quite niche. So it's really looking at an unstudied type, which is flats, in particular with a specific type of heat pump, because the performance really matters. We've got lots of flats and we've got lots of people who don't have much money living in flats, but we don't know how those systems perform. So that's kind of what we're looking at the moment.
Yeah, because the heat pump, its efficiency changes with the outdoor temperature and the load, so it's a much more difficult thing to assert to a prospective client or someone who wants to have it installed in their home. And is that uncertainty between the model version, model predicted efficiency and what's actually happening? Is it you mentioned they're equal to a resistance heater, but what is the on average? How much more below does it perform?
It really depends upon the specific trials. It's really difficult to put a number, just a number, but I would think that there shouldn't be very many heat pumps in the UK that are performing worse at a coefficient of performance of 3 at the moment on over a year, which is 3 units of heat for every 1 unit of electricity.
Okay.
There are bound to be some, but
yeah,
should be rare.
Thanks, Cliff. So your final slide, but one, I think, was your learnings. I'm kind of interested in, if we think about the rate that the government would like us to move on decarbonising heat in the built environment, it feels like many of these elements will be necessary to deliver at speed. And I'd be interested on your reflections on, to what extent should we be thinking more about sort of modularised approaches? The condensing boilers was kind of almost a like-for-like replacement, and it kind of worked, and that was great. But then some of the other interventions are much more bespoke to individual buildings, much more labour-intensive, many more actors. I mean, if you were thinking about a strategy, if government came to you and said, right, how do we deliver against these targets at pace in the built environment? What do you reckon? What's your pitch for where we should go with this?
Thanks, David. Well, one very quick point is that you mentioned just changing the boiler and so on. Things like changing a heat pump is when you've got a point of intervention, what else could you do whilst you've got disruptive works going on? So being a bonnet that I've got at the moment about heat pumps is that when you have a heat pump installed, they don't offer you a new a replacement for your gas cooker, which is also subsidised, or it's the perfect intervention to get somebody off gas. Yet, if you want to get disconnected, they won't even do that for you necessarily. They certainly won't offer to change your gas hob for a new induction hob. And you've got this perfect intervention point, and yet it's not being taken. So I think there needs to be a bit of joined-up thinking of the path. And I think the problem with that is government is focused on the pounds per carbon saving. But points of intervention don't work like that. You do something big like the heat pump, which makes sense, which is a good investment for pounds per carbon saving, whereas replacing a gas hob isn't, but you're in the home. So it never looks good on the economic models, and therefore it struggles to ever stand any chance of getting into policy. But it's kind of crazy not to do it at the same time. So I think because so many of these things are interlinked when it comes to buildings, looking at somebody's doing something, what could we offer them at that point to add up to better outcomes? Did I remotely answer the other bit? What was the other bit?
Yeah, I suppose the other bit is, we've seen this plummet, I suppose, in the costs of various technologies, particularly like PV and batteries. So So if the challenge is kind of like decarbonising, should we be thinking about a kind of a suite of technologies like PV on the roof, a battery in conjunction with heat pump and other elements? So we're looking at this kind of ensemble of things that can work as off-site manufactured bits kind of plugged in, rather than thinking of the traditional model of we go in and we kind of renovate and insulate and all of that. How's that sort of balance shifting through time?
Well, I think you're right. I mean, I think the balance is very much shifting towards new whizzy tech. It's less disruptive. I think as battery costs come down, they'll be very common. And I think that's, to some extent, that's going to be fine for some people. It's really not necessarily good for the fuel poor. If you're fuel poor, the best way to help you is to insulate your house. And then it's just warmer. You don't have to pay for keeping it warm. So so it might work for some homes. And then you've got the network challenges of, the problem is you don't see the benefits. But if you reduce your peak energy demand and it helps them not have to upgrade the local distribution network, that's great. But how would any householder be incentivized to do that when retrofit is really expensive and it's really difficult to make a financial case for it? And there needs to be some kind of linkage.
Cliff, thank you so much for your lecture this evening. It's been a real pleasure to listen to you. In a moment, I'm going to invite you for drinks, refreshments outside, but I'll just share a couple of reflections, if I may. Cliff, you really warmed my heart this evening when you were telling us about your boring paper, actually. I'm really reassured by that, because I can write some really boring papers now. Thank you for that encouragement. But more than that, I really liked, the meticulous, the thoughtful nature of your work, the way that you zoom in on the technical detail, then you zoom out to policy. And I'm not surprised to see that lovely list of recognition, the awards that you and the team have received. I think that's really great to see. And I kind of wish you luck in your search. I'm thinking of you as Doctor Who now, in the TARDIS, through your universe, trying to find this perfect method. So please continue your journey. Good luck from me. Thank you so much, Professor Cliff Elwell. Good evening.